All right. Well, so I'm Bob Zwask. I think I know most of the people in this room. We are presenting some of the work that's been going on in AF2 accelerators for neutrinos. So it was decided this time for Snowmass to have a group that was dedicated to thinking about accelerator issues for neutrinos. Whereas in the neutrino frontier, there was the artificial neutrino beams who thought about some of the neutrino beam issues. So neutrinos are such a high priority. I think it's good that we had a group that was dedicated to this. It did make it complicated, as what we're talking about for the most part is multi-purpose facilities, and well, some of those other purposes were not directly represented here, but we'll talk about them a bit, and certainly we coordinated. All right, so whoops. So two got combined there. So sorry about this. It's been a very busy week. And so this is going to be not a comprehensive report, but I think it'll give you the status of where we are now and have some of the emergent themes we've identified. So I'll start by talking about just AF2 a little bit more general and what we've done. Go through some highlights of contributed LOIs and white papers. And then what's supposed to be next is then some discussion of the neutrino program at Fermilab, and that's specifically PIP2 and its successor accelerators. Some emerging themes that came even just this week on some of the choices for these accelerators. And then one of our deliverables was also a number of summary tables of needs and capabilities. And so the needs were the needs of the neutrino community, and some adjacent to the neutrino community. And so thank you to the Neutrino Frontier for helping us put together, and then capabilities of the accelerator community, both present and anticipated. And here, I'll just take this off if you don't mind. All right, and then a little bit about our plan forward. And we've had a lot of good discussion this week already, particularly at our Wednesday session and in the hallways. I intentionally left plenty of time for open discussion, and because I just couldn't integrate all the information from Wednesday, I think we'll have plenty of time. All right, so AF2 accelerators for neutrinos. This is kind of our mission that we wrote for ourselves in the beginning, so over 2 years ago. So we want to take as input the anticipated needs of particle physics and the requirements for neutrino beams in terms of energy, flux, temporal and spatial characteristics. Some of these issues helped us really narrow down the options for accelerators. And then what we produce is, first of all, the proton or other beam requirements that are necessary to meet the neutrino physics community needs. And of course, we deal mostly with proton beams to make neutrinos, but there are other possibilities as well. And then again, we'll going through the capability of existing or planned accelerator facilities that might satisfy the above, and then identify some areas of R&D or development or technologies that might be necessary to move to this next stage. The conveners of this group were myself, and then John Luigi Arduini from CERN, and John Galambos from Oak Ridge. They weren't able to be here this week. They have been online in a number of our discussions. And then I'll have more about this, but we have what we consider now a complete draft of tables of worldwide needs and capabilities of accelerators for neutrinos. And so that's a number of tables. Earlier versions were shown on Wednesdays. I have more complete versions today with all of the Fermilab upgrades included on it. Our draft report right now, it has an executive summary and some notes, particularly about the white papers, and a draft report narrative. That's going to be extensively updated after this meeting, in just a few weeks after that. Oh dear. No, so there are closed caption. Let me close that. Is that okay now?
Yeah.
All right. Okay. All right. So again, there's been a lot of discussion this week. We're soliciting comments. Right now, this is a perfect forum for right here or offline to us, well, through email. We have a mailing list for AF2 announcements. I know some people here are on it. We plan to distribute the the draft final report through this in the next couple of weeks, and then have a mechanism for getting comments at that point. All right, so what was our process in AF2? Well, of course, we had LOIs and white papers like everyone else. We had a few plenary sessions. These were just online meetings. There were a few seminars. There was a town hall. Of course, we had the community planning meeting. We had a joint session with Neutrino Factory. We had explicit attendance at about 12 workshops over the last 2 years, some on neutrinos and some on accelerators. And so that was a good way of developing input, and also trying to find white paper submitters. We coordinated with both AF5, the Rare Processes and Physics Beyond Collider group, and NF09, and there was especially the tabulation of the neutrino beam needs. We had a number of sessions here at the CSS, and the Wednesday one in particular, there was a lot of discussion. All right. Okay, so where we curiously had both 17 LOIs and white papers, depending on how you count them. So there were 17 LOIs directly reported, directly submitted to AF2, and there were a mix of facilities, concepts, and technologies. There were many relevant LOIs in other areas. I didn't count them up, but so the true number of relevant LOIs would be much larger. So a significant number of these LOIs did not result in white papers, but they still provided valuable input. For the most part, they took part in our town hall and presented some slides. So some of this input still made it into the final report. We then had 17 directly relevant white papers. They weren't all submitted to AF2. There were quite a number of papers that were just submitted to the Accelerator Frontier, and some of the AF5 papers were relevant as well. And we certainly got a significant amount of input outside of the white papers, especially when we were tabulating facility capabilities and needs outside the US. Okay, so just a few highlights on some white papers before I get to the Fermilab program. So there is a lot of innovation in the neutrino area. Certainly our long baseline beams are not the only way of doing neutrino physics, and the neutrino area has become so large that we're looking under every nook and cranny to find neutrinos. And so CERN has indeed found neutrinos from their collider, from the LHC, and this is a very interesting approach. Certainly, I think people knew that there were neutrinos being produced at the interaction points, that there's a lot of relatively soft or produced pions and kaons and other particles that do have a chance to decay. So it's kind of an exciting use of what's a free source of neutrinos, and there have been the original phaser experiment has detected neutrinos from these collisions, and so this was. So we have Atlas here, the collision region, and then a direct line of sight to other areas, which other rings, other portions, other tunnels where this detector could be put. And so the principle's been proven in experiment now. I think that and it's been developed into what's called the Forward Physics Facility, which is a very aggressive search for both looking at neutrinos and other dark matter candidates that could be produced in these types of interactions, and then pass through a period of Earth that acts as a filter for all the charged and conventional particles. For us, there wasn't much to say here. These come for free, and there's really not much you can do with the accelerator to optimize these. There's no real decay pipe or focusing of these particles. They're focused purely in the forward direction, in either direction. And then, as soon as they come to a dipole, they're not as stiff as the protons, and so they're all lost. So it's actually the interaction region of the experiment itself that is the decay region. So there's not much to say for accelerators. Otherwise, the only source of this are going to be very high energy hadron colliders. So things like the EIC or E+, E- colliders, they certainly produce neutrinos, but the numbers are going to be vanishingly small in comparison. The source neutrinos here is still very similar to what we have in long baseline beams. pions, kaons, and the like. All right, so another major proposal out there in the world is at ESS, ESS neutrino superbeam. And this proposal has been evolving over the last several years. And it just kind of starts with kind of the obvious issue, the obvious opportunity that there's a 5 megawatt source that's being built in Sweden, and you know it's going to be used to make neutrons primarily. But what are the options for making protons with this? And so they've developed their proposal through several iterations, but it's still a major facility investment that would have to be made. It involves upgrading the LINAC energy. The ESS is 2 GeV, so it needs to be pushed to a little bit higher for pion production issues. The rate of the accelerator needs to be doubled, which means a lot of the RF also needs to be upgraded. The ESS accelerator is actually a proton accelerator. There's no accumulation. It directly puts its beam into the mercury, the tungsten target to produce the neutrons. So it needs to be able to produce H-, and the concept is on alternate pulses, protons will be produced or H- will be produced, which of course makes the LINAC a little more complicated. You cannot reliably use dipoles to bend the beam, for example, because they will bend them in different directions. But you know, this approach has been demonstrated before. Los Alamos did it on their LINAC. In fact, they did it on single pulses using the 180 degrees out of phase RF. So it's something that's certainly potential. You know, that's certainly possible. But then the pulse from this LINAC is too long to really be useful enough. It needs to be accumulated, and that's a theme that we'll have in the future as well at Fermilab. And so they have designed a relatively compact accumulation ring where they build up the charge, and it's about 14 hertz, and then deliver it to a target station. This target station is smaller than the ones you might see at Fermilab or JPark. The reason for that is because of the much lower energy, the 2.5 GeV. In fact, the energy is so low that and the beam power is so high that it makes it pretty much impossible just to have one neutrino beam line. And they actually split their beam into 4 separate 1.25 megawatt beams. And that's kind of what you see here. This is the switch yard, where in subsequent pulses, beam will be switched into 4 different beam lines and go through collimators. And then they would come into this is their target station here. And then they have a bank here of targets and horns. And so what you're looking at here is the downstream end. So 4 separate horns with 4 separate targets inside of them. And this makes it at least possible to do. And so this concept was taken or adapted from CERN, who considered this for their superconducting proton LINAC that could drive a neutrino beam. You know, something like this is certainly possible. The large power supply has to switch between each horn each time. It adds a lot of complexity, but it's still possible. And then not really our area, but there's a new megaton scale detector that would be needed with this, and also a near detector on site. So, you know, this is, even though it uses the ESS LINAC, it's, you know, almost a greenfield project. And some of these challenges that we have here with, you know, intense accumulation ring, the target tree, and other issues, it really it illustrates some of the challenges of multi-megawatt beams and being able to handle them. And really what might be the limit of horn focused beams. You know, this approach really looks at, you know, it looks like it's at the limit of what's possible. You know, it's, you know, it doesn't appear like there's any, you know, technical things that might jump up and be and obviously stop you. But you know, the complexity here is just so great, and the subsequent cost, that it makes you think twice. And then if you wanted to go to 10 megawatts, it looks like just not possible anymore. So we're kind of coming up against that limit. You know, what is it? Is it 5 or 10 megawatts? You know, I don't really know. Also, it depends on the beam energy. So for example, with the Numier LBNF beam that we have at Fermilab, the beam's 120 GeV. And so if it's 60 times as high, that means that there's 60 fewer protons for the equivalent amount of beam power. And that makes the targetry much simpler. That makes the horns a little simpler. And in fact, if you go back to look at what CERN did with CNGS, they were operating at 400, 450 GeV. And in that case, their target, which still operated at a few hundred kilowatts, didn't require any active cooling. It was a passively cooled target. So going to higher energy is still a possibility. Of course, when you're dealing with these really high power LINACs, going to high energy is expensive. All right, so it's just some interesting lessons with the ESS. There are some alternative approaches here, and I'm not going to go through everything, but just highlight a number of things that are distinctly different than what's going on at Fermilab or JPark. And so there's the ISODAR Daedalus program, and it's not limited to just these two. There are other options as well, but the idea is to use high power compact cyclotrons as neutrino sources. And the issue here again is that cyclotrons generally don't go up that high in energy. 1 GeV starts to become prohibitive. So you're not going to have multi-GeV beam, but they are very close to they are CW beams, and they can produce very high beam powers, as we've seen at PSI in Switzerland, for example. So their concept here is to build a much more compact accelerator. Also, some other innovations like using molecular hydrogen rather than just H- ions. There's a number of approaches that they're there. And so the pilot is a relatively low energy one, what would be an injector cyclotron called ISODAR. It operates in the multiple tens of MeV. And their approach there is actually to produce a very intense lithium-7 decay source. And so here, what's kind of shown is that this would be underground near a detector. And they are actually planning to deploy this at a lab, underground laboratory called YemiLab. And they just through the nuclear interactions and the production of neutrons, they would they use lithium-7 to make lithium-8. Which decays relatively quickly, and put that near a very large detector. So that's electron neutrinos produced pretty much at rest. The upgrade to this would be another decay at rest source, but now producing pions. So the Daedalus experiment would be that, something in the few hundred MeV to GeV range that would produce a significant number of pions. It's still not necessarily optimal for pion production, but if you're just going to stop them, it's pretty effective. And then just produce an intense kind of megawatt class decay at rest source. Some of the challenges with this is that it is a CW beam, so you don't get the timing information that you might like. And of course, if you're depending on decays of longer lived isotopes like lithium, you lose any timing at all. Let's see, so something else that's been around for a long time, but is again qualitatively different, is the neutrino factory. So the neutrino factory physics case has been updated with the newer information that we have over the last 8 years of experiments. Experimental results. Their conclusion is that the case is still there. And so they produced a relatively compact physics case document. The technical approach is pretty much the same as previous designs. If you recall, the original purpose, one of the original purposes of the neutrino factory was to look for extremely small theta 1-3. That if it was very small, our conventional beams would have a challenging time producing that. We now know theta 1-3 is large. In fact, we've known that for about a decade. But the neutrino factory offers the possibility of more precise measurements. The flux in principle can be known much better. And if there are anomalies that may emerge from experiments, this would be a good way to approach them. And then, of course, people who want to build a muon collider, they see a lot of synergy with it here. So this option is out there. Again, the machine isn't being aggressively pursued by anybody, but it remains an option, especially if we're coming to the end of conventional beams with LBNF and T2K and possibly ESS. then this is the kind of thing that might be next. And there are other ideas, other more unique ideas that operate at lower beam power. I didn't put them all in there, but here's one, ENUBET, which is being at least explored at CERN, and they call it an enhanced neutrino beam from can tagging, or it's a monitored neutrino beam. And this is kind of a step to what's always been kind of dreamed of a tagged neutrino beam, which is extremely challenging to do. And so in this case, they look at just the kaons to get kind of an absolute flux determination of the beam. There's a lot of subtleties there, so this certainly hasn't been demonstrated yet, but it is something that could potentially be done and useful for neutrino cross sections or short baseline experiments. There are some accelerator requirements for this in terms of timing, but otherwise it's pretty achievable. They're not trying to go to very high power at first. If they wanted to go to the next step of a tagged neutrino beam, it really involves identifying each and every decay individually and correlating that with the detector. And considering that you have to produce on order 100 trillion neutrinos to detect one in your near detector, it's pretty challenging. The scale, this is about 50 meters here, I think. Okay, so let me get to Fermilab a bit now. So certainly this is an active area of discussion in SNOMAS. Trying to help Fermilab, adapt its facilities to be used optimally. Yeah. So what's underway now is the PIP2 LINAC and other upgrades associated with it. So it's a superconducting LINAC, 0.8 GeV. I'm not going to step through all the details, partially because it's just too cumbersome to put them all into new slides over and over. But it also includes synchrotron upgrades to our booster, main injector, and recycler to a lesser extent. And its primary purpose is well understood. It's to provide 1.2 megawatts to LBNF, and it's being built to that. But at the same time, there's a significant amount of a GeV beam available to other experiments from the booster, and up to roughly about 1.5 megawatts available at 800 MeV with a little bit of extra work. And the experimental use yet to be identified. So again, you might view this as really a single purpose accelerators to provide 1.2 megawatts to LBNF, but it has a significant amount of additional possibility. And so we're at the point now where the project is fully under construction, and it's to be complete and commissioning in 2028. And the intention there is that's a few years before LBNF is ready for beam and allows it to be commissioned up to 1.2 megawatts at almost day one of LBNF. So there's this question of exploitation of PIP2. And so this is an accelerator question, but it's highly correlated with who's going to use it. Only a small number of the lower energy users are neutrinos. Certainly there's a lot from AF5 rare processes that are interested in this as well. So this is a bit of a puzzle right now, but we can talk on the accelerator side of a number of things that could be considered kind of an experimental build out of PIP2, of actually being able to provide beam to these experiments. Because we know that there's a large amount of beam available to use, but actually when PIP2 is built, there will not be much in the way of beam delivery or formatting for experiments. In fact, its only connection on day one would be directly to the booster accelerator to produce higher energy beams. And so, some things that can be explored in terms of R&D and eventual implementation are listed here, and I don't have these linked up to experiments, but you can kind of, you know that a lot of them are interested in pulsed beams, and so there's a question of can the LINAC run at low duty factor, meaning high compression running, and just directly provide beam to experiments that is more useful. So high power beam with low duty factor, it's not really built for that. PIP2, while the LINAC itself will be CW capable, there are a few components that are missing to produce CW beams, and one is a fast chopper, CW compatible. To make one of the ideas of PIP2 was that it be a digital beam that each and every pulse could be chosen to be on or off. Generally, the intensity is not adjustable, but at least the beam on and off was to be possible. But that the chopper that's in there right now is really more optimized to just providing beam into the booster. So that's something that would have to be implemented. There's a lot of interest from us, and I'll get to this a bit later too, about higher currents. It's either high peak current or high average current. The PIP2 LINAC will be at about 2 milliamps. It's believed that it would be relatively simple to push it to 5 milliamps, and then there are even options beyond that. And that could be either average or peak power, depending on how much is going to be spent. And this makes a lot of the issues of using this beam a lot simpler. The very low current of 1 or 2 milliamps is extremely low for injecting into a synchrotron. Usually that's done at 30 to 100 milliamps. And so it makes the injection period much longer. It makes the issues of stripping much more challenging. And so all of that could be helped by going to higher peak current. Another that was discussed is that there are concepts for RF beam splitting, and this is that subsequent pulses could be split down a switch yard and sent to different experiments. The idea has been around for a long time, and it usually involves a transverse deflecting cavity. However, that's not presently in the PIP2 scope, and there's no really active design going on that. So that's something that could be developed as well. There's also a need for fast switching magnets. So for example, if the full beam were sent to the booster for a period of time, and then you wanted to send it to the switch yard, you would have to be switching between them. PIP2 doesn't presently have those. And then we'll have more discussion of accumulator rings, or compression, formatting, for compressing the beam, formatting the beam, slow extraction. And that was discussed this week as well. One idea that's been out there for a long time is to directly inject or directly send PIP2 beam to mu to E. As someone who from the target community, I have some sincere questions about whether that's a good idea. Again, this issue of lowering the beam energy from 8 GeV to 800 MeV makes the targeting much more challenging. Is that a question?
Yeah, direct PIP2 beam to mu to E or to mu to E2?
Well,
the bullet we are reading now.
Okay. So Vladimir asked what exactly is meant by direct PIP2 LINAC to mu to E. Is it mu to E or mu to E2? They're a bit mu to E. So I guess I'm saying the mu to E facility there, right? So I think. I'm sorry.
It is mu to E2.
Yes, but.
E2 is by definition sending PIP2.
Right. But or you have a new facility, which some of us would believe but might be much more valuable. But that's not really a question for our group.
It's a question to Eric and Bob. Is it possible to send PIP2 beam to mu to E as current?
No, I mean mu to E2 is a very specific proposal to send PIP2 beam directly to to the mu to E facility, but it requires significant modification. We're talking about things beyond that. Mu to E2 might never happen, but that is the mu to E2 proposal.
Right. So if we'd want to pursue that, a direct link would have to be built. And there's other ways to do it. Things like transfer lines, they don't exist either, other than just to the booster and the absorbers. And so, there's many other options. There's a lot of beam there. And really this needs further input on experimental preferences. We have a lot of information here at Snowmass. We don't have much on differentiating the priorities between those, but a priority should be to get clear on the experimental preferences, and that's also an issue for PIP2 successors. Okay, so let's get to those. The PIP2 successor is now being called PIU at Fermilab. Don't write that in stone. These names have a tendency to change, but it's now called the proton intensity upgrade. And kind of like we said, LBNF has become a single-purpose accelerator, or PIP2 has become a single-purpose accelerator in the short term. this PIU is as well. So it's one fixed point at this time is that it will provide 2.4 megawatts to LVNF and complete the vision from the previous P5. There's a lot of support to try to get started on this effort and in fact, to try to be finishing it by mid to late next decade, which means that, you know, the design choices will start coming very quickly. All right, and so there are very significant questions about what the accelerator options are, the basic geometry of it, and what the desired other capabilities are for additional experiments. And so that needs to be cleared out. And so we spent a lot of time on this at Wednesday. There were several different presentations, and that's a good place for information. I started copying a lot of it into this talk, but it just ended up being too ugly. So I have a very kind of high level observations on that. Okay, so there are two basic options for evolving the Fermilab complex beyond PIP2. And so if we start with what we have now, is we have the fixed points are that there's a PIP2 LINAC that's being built up to 800 MeV, CW capable, and that there's a main injector which can go up to 120 GeV. And everything else is a little bit unclear. The LINAC can be pushed up to 1 to 3 GeV in this case, or in this case, you can have just an entire 8 GeV LINAC which delivers beam to the main injector. So in this case, it's a LINAC and a new booster replacement, a rapid cycling synchrotron. And then there's also questions of whether you want additional storage rings. And there's a number of reasons for that. At high energy, we use the recycler now to make the acceleration to high energy more timely, so that we can get more beam power. At low energy, there's a number of reasons you might want it. A number of the experiments have a preference for very compressed time structures. And so it can be compressing the beam for that. It can be a stripping ring for the RCS. And so you have a custom ring, or a ring that is custom designed to be optimized for stripping, and therefore make the job of the RCS simpler. There's a number of options here, and it makes it a little complicated. I think I have a slide on that. And so the LINAC version, the options here, still you probably need storage ring at some point, some kind of compression ring. In fact, I think that's one of the conclusions that I'll get to in a moment, is that all of these options need a ring of some sort, an RCS, a compression ring, a storage ring, and maybe multiples of them. So it's not as simple as just building cryomodule after cryomodule, getting up to 8 GeV. There needs to be some other type of storage ring that makes it useful. And then you know, one of the ideas, so rather than wait till the end to have these storage rings, these accumulation rings, one idea out there right now is to have a proton accumulation ring. This has previously been known as the booster accumulator ring. And then there's a more compact version as well called CPAR. But this would be even before the PIU, perhaps with PIP2 itself, to put a relatively compact accumulator ring that can be used for experiments and for injection into the booster. It's small, not necessarily enormously high current. You know, one of the issues with this is how does this scale? You know, as we're going to higher energies with the PIU, you know, does it work at 2 GeV? You know, will it work at 8 GeV or the other energies we might have? So there's experimental questions there. There's practical questions there. You know, how many of these rings will we build? Also, you know, the requirements for this ring vary a lot on what the experimental uses are. If it's just a stripping ring for the booster, you know, we're talking about, you know, about 10 kilowatts, okay? But if it's the first phase of these experiments here, we're talking, you know, more like 100 kilowatts. So the second phase is more like a megawatt. And if you're stripping a megawatt of H minus versus 10 kilowatts of H minus, it makes a big difference in how you might build this ring. All right, so some of the emerging themes. So as I mentioned, at least one ring will certainly be necessary in all scenarios. And so, you know, it's an accumulator, a compressor, or an RCS. And we might need to have multiples of those. And so one of the outcomes is that we need to have some emphasis on beam dynamics, RF cavities, because every one of these rings will require RF cavities, and other issues that are specific to rings. So the PIU will not just be LINAC upgrades. And we also know that many potential experiments require short bunches. There's this question of can rings be upgraded or reused at higher energies? And there's this issue of stripping, and it becomes a challenge at high rate, and in fact, at higher energy. This stripping cross, if you talk about going to 8 GeV versus 800 MeV, the stripping cross-section actually goes down a little bit, but the lost energy goes up because the beam energy is higher. So foil stripping becomes more challenging, and especially again, if you're doing a megawatt, it becomes challenging again. What do we know? We know it's possible, right? So the SNS right now strips over a megawatt of GeV class beam, and they plan to do more. So it's certainly possible to do that. The differences are that places that have the high intensity beams like SNS or JPark, they have pretty extensive foil development programs to produce their own customized diamond foils. And the other issue is that those rings generally just have much larger aperture than we would have. The produced beams have much larger emittance. And so a lot of the heating that comes with these foils are through parasitic interactions of the circulating beam with the foil and not the injected beam itself. And that also gets, that issue also becomes more challenging when you have a low LINAC current. And so all those issues add up to make it look that stripping becomes really challenging at high rate. The good news is that there's a fantastic technology out there using lasers to strip the beam that would have markedly lower losses, but it's not a magic wand. It requires very high energy photons to knock off or to excite electrons on hydrogen, and it's a subject of development at SNS and JPark. Fermilab has not worked extensively on it, so that's something that Fermilab is not doing. The good news is that it gets substantially easier at high energy. So in the rest frame, the energy needed of the electron is deep into the ultraviolet. However, you get the advantage of the Lorentz boosting. At 400 MeV, this is an almost impossible journey. At SNS energies, it really depends on what lasers are available, but it's a very challenging issue at SNS. However, if we are at higher energies, 2 or 8 GeV, it gets much simpler. You get to the point at 8 GeV, in fact, where an infrared laser could be used. And those are certainly much more available. They're safer. They have higher power, higher efficiency. This could be a very active area of research. And then, as I've said a few times, LINAC current increase is also potentially very useful in terms of stripping, injection, and the experiments as well. Okay, a few more themes. We talked about for an RCS, these issues of injecting into sinusoidal magnet excitation curves. That's how it's been done at the Fermilab with the booster for many years, and I think it's just kind of adapted as the default for an RCS. But I'd say it's really not necessary. The JPark RCS operates with essentially a flexible power supply, switch power supply at 25 hertz. It has flat, more or less straight acceleration, linear acceleration periods, and then it's flat at flat top as well. And that's certainly something that could be implemented. And if you have a power supply that's not synchronized with the frequency of the electricity coming into the site, that also has other advantages as well. So I think that's really something that could give you a more stable accelerating platform as well. There was some discussion of FFA options. These really have not been explored much at Fermilab. It has been explored in the UK for ISIS. There's a lot of questions about whether this makes sense, but that's another issue for that's another way to fix this injection issue, at least partially. There was some discussion of the main injector cycle time, that it could be further reduced, and that kind of gives you more beam power without having to have more intense beams. And so it's almost all advantages there. I'd say just from a targeting point of view, the disadvantage is that we have to pulse our horns more frequently. And that's, for most of the horns, that's the major source of of heating and stress in them. So it's not necessarily a magic wand again. There was more discussion about energy consumption and what we need to, and that we should consider that. We know that the PIP2 LINAC will consume significantly more electrical power than the existing LINAC and booster, but it will be able to produce a whole lot more beam. Okay, and so how that trade-off works is kind of questionable, or is not so well understood. And when they, when you go to a pulsed LINAC, as you might for the higher energy, that will be more energy efficient than the CW LINACs. So there's a lot of questions there, but we know the PIP2 LINAC will be, somewhere between a quarter and a third of the energy consumption at Fermilab. And so if we're talking about significantly expanding it, we have to think of, about the infrastructure and just the sustainability of these accelerators. Finally, these aren't in the options right now, but it's something that has been considered before and is well known. And that is that we've had some discussion about the emittance of these beams and how places like J Park and SNS get the very high power because they're able to have large emittance beams. And we are limited right now by the injection emittance to either the recycler or the main injector. Okay, that kind of sets the scale for the emittance of everything upstream and downstream. As you accelerate beams, they shrink due to, well, we call it adiabatic damping, but really they're just getting Lorentz boosted, and so the main injector actually has larger acceptance for emittance at higher energy, and so it increases most quickly at the lower energies. So if you could inject at 10 or 12 or 16 GeV, you could reuse the main injector much more substantially and get the higher intensity beams. And that opens up the question of the recycler. The recycler is a permanent magnet ring, so its energy is not adjustable. So either if you were to pursue this scheme, either the recycler would need to not be used at all, or it could be replaced with a new storage ring. And even though it's a large ring, it's using permanent magnets, it would be inexpensive compared to an entirely new synchrotron with like the main injector. All right, so some programmatic considerations that have become more clear also over the next few years. And that's first of all mu to E. So mu to E will certainly run at 8 GeV with PIP2. And so what this means is that, again, is that the PIP2 beam is not directly going to mu to E. We're going to use the existing beam delivery, which means the PIP2 beam goes to the booster, which then goes to the recycler and to the mu to E experiment. And it'll be limited by its slow extraction. So it'll continue to run at its roughly 8 kilowatts. It does have a potential impact on the beam delivery to LBNF. So presently, when mu to E runs, because of timeline issues of beam sharing between the different users, it actually makes the beam power to NUMI about 15% lower. And that could potentially be an issue with LBNF. The choice was made years ago to try to push the booster to 20 hertz operation, and that at least partially ameliorates this. So that 20 hertz is important for that. And then what will mu to E do in the future? For example, in the PIP2 successor PIU era, that really depends on what the experimental options are. There is this idea, of course, that was discussed of sending 800 MeV to the mu to E experimental hall. I do think that there are some pretty substantial questions on whether that's a good idea. And there are other newer muon experiments being proposed. Just another note on programmatic. So the BNB, the boosted neutrino beam in the short baseline neutrino program, it's presently not planned to run. And I don't believe there are any new white papers on that program. They're planning to finish up their experimental period prior to the implementation of PIP2. But that being said, we plan to maintain the capability to run beam to the booster neutrino beam after the PIP2 implementation. And there's a number of reasons for that. First of all, if these experiments find something remarkable, we probably will want to look closer at them. Also, there are some ideas for how to use the booster neutrino beam as a beam dump experiment for dark matter searches, for example. It presently doesn't interfere, but that'll depend on what the experimental path is. Okay, so a little conclusion on the proton intensity upgrade. So again, the driving force here is this 2.4 megawatts to LBNF. It's the highest priority for the PIU. And maybe the downside is there's multiple ways to get there, but it's also an upside. We have different ways to do it. They all look achievable. They need to be understood in terms of their cost and practicality. And Fermilab does intend to rapidly develop these designs over the next few years. And as of now, cost will be a primary driver because these different options could have significantly different costs. However, as we've been discussing, other experiment options could really make a big deal in terms of the design choices for this accelerator, and understanding these would be very helpful. All right, so here are the tables. I showed a version of these on Wednesday. They're mostly the same. They've had a number of updates and corrections to them. There's a few other updates that we'll do, but most of the substantive information is there. What we're looking at here, and this came mostly from the neutrino frontier, is the existing neutrino beams or ones that are under construction, and the anticipated proton beam that drives them. And so we have the NUMI beam at Fermilab, the BNB at Fermilab, the T2K upgrade, LBNF Dune, along with a number of kind of options for it. These numbers are relatively understood. Phasers put on here as well. Again, that's production from the LHC collision region. And then there's a few others put on here. And these are, well, they're actually all neutrino sources or neutron sources of a type that are used for most substantially recently. They've been used for detecting coherent interactions, but there's still a number of other interesting experiments that can be done on these, beyond standard model physics, sterile neutrino searches. And so those are all kind of existing facilities already underway, not necessarily optimized for the physics, but certainly useful. All right, so there are further proposed beam facilities. And so here we have some of the PIP2 beam dump experiments, the SBN or BNB beam dump experiment, both of those at Fermilab. There's ISODAR, which we discussed, ESS, neutrino super beam we discussed, a different version of that based on NuStorm. There's, where you would go if you went, if you had a TeV muon collider. And then NuStorm again. Moment is a proposal that's been out there in China for a period of time of using a very high energy, high power accelerators that are being developed for accelerator driven systems. And so if this accelerator was available, it could create 15 megawatt beam. The concept for this has not been updated much recently, and it really depends on accelerator developments there. Of course, the targetry is different. They do have a concept for that. So there was a substantial amount of work on that. And then also ENUBET, which we discussed earlier. Okay, and so the existing Fermilab, or the existing accelerator facilities, we put them here mostly for completeness. So CERN, of course, has quite a number of accelerators that are capable of producing neutrinos. Well, the one being used at the moment is the LHC, but the other ones are still available. Here's CSNS, the Chinese spallation neutron source, the present Fermilab capabilities, the present JPARC capabilities, and then capabilities that you might have at different locations at Los Alamos, at RAL, at PSNS, at PSI, at SNS, and at Triumph. All right, so the planned upgrades. So the substantial change from Wednesday here is we've really filled out the Fermilab PIU options. Brookhaven has had some proposals around for a while. They have their isotope producer, and they're likely to do a modest upgrade to that. They've had a more substantial proposal out there using Blair, which might have used a FFA accelerator. I don't think there's been much progress on that recently, but it remains as an option. The Chinese spallation neutron source is likely to have an upgrade. ESS is being built, and they have their neutrino option. Here's the many Fermilab options now. So we separate out special into the PIP2 and the PIU phases. And so with PIP2, there's the LINAC itself, which we put here is up to 1.6 megawatts. Of course, we don't have a way to use that right now. There's the booster in that regime and the main injector. Then we step up into the PIU and the various options that are available there. So there's what we call a low energy LINAC upgrade. And so this, and there are options for this. This is increasing the kinetic energy of the LINAC up to 1.2 to 2 GeV, and it would probably be still CW at that point. Its current could be upgraded to as much as 5 milliamps. And if you would really do that, 5 milliamps at 2 GeV, that would be 10 GeV, 10 megawatts of beam available. So that's something that's possible. And so this low energy LINAC upgrade, some form of it is generally a predecessor to the other PIU upgrades. Then we have the options. So there's the LINAC options at first. So generally the intention is to produce a pulsed LINAC. And the reason for that is the pulsed LINAC operates at higher gradient and higher efficiency than the CW LINAC. And so you would, it's much less expensive to implement. But what you have is then you no longer have the CW beam. And so, then at this point at 8 to 12 GeV, you have somewhere between 0.4 and 1.2 megawatts. That's quite a large number, but is it a disappointing number knowing what the CW LINAC can do? And so if you were to go with a CW option, which is not the primary option right now, again, if you were to push to 10-ish GeV, and if you were to push the current as well, you very quickly get beyond 10 megawatts. So that's, again, an interesting beam, but it's not necessarily formatted how you would want to use it. And then another option, the RCS version of it, which is kind of more conventional for what Fermilab would do. And so that would involve first this low energy LINAC upgrade, and then an RCS that would bring you somewhere 8 to 12 GeV. Its beam power is similar as to what you would get out of a pulsed LINAC. And so, again, the question is really, is there a multi-megawatt user at 10 GeV that would motivate something different? All right, and then if you take that to the main injector, again, here's this fixed point, 2.4 megawatts to LBNF. We know that's what we want. In discussion of the options, there are people who are pretty confident that, if we change some of these other things, like we really got the most out of our LINACs or RCS, if we increase the injection energy, you could easily imagine being able to provide 4 megawatts in the main injector. We don't know if LBNF can be upgraded beyond 2.4 megawatts, but this could be used for other purposes as well. We then have the accumulator rings, so that there's quite a number of options here. So this is just considering applying them to experiments, and so there's kind of two versions of this that are mostly out there. There's the PAR and the CPAR. And so the way to think about it is the PAR is a way of accumulating a ring, which is mostly the circumference of the ring, maybe lower by a factor of 4 due to bunch rotation. And so you get pulses of less than 1 microsecond, probably more like a few hundred nanoseconds, or 2 times 100 nanoseconds. And then the beam power of that is probably limited somewhere between 0.1 and 0.4 megawatts, depending on the parameters and the uses as well. CPAR really is a much more compact ring with the intent of getting to very short pulses, in this case 20 nanosecond pulses, and then also trying to simultaneously use as much power as possible, perhaps up to 1 megawatt. Both of these experimental uses are at around 1 GeV. Okay, and then here's some of the other ones we discussed. We discussed ISODAR, making lithium isotopes, Daedalus, making pion decay at rest. The hope, of course, with Daedalus, it's been a hope for a while, is to make cyclotrons so cheap that you can just make several of them and put them at different locations from your detector, and therefore do kind of intermediate baseline physics. The HL-LHC will also produce more neutrinos than the LHC as the luminosity is raised. ISIS upgrades are being considered, including again the RCS or an FFA. So there's potential beam power available there, and they certainly have a history of doing particle physics experiment, even though they're mostly interested in producing neutrons at the moment. JPark has a number of upgrades underway, really, and their main ring with fast extraction is likely to get up above 1 megawatt in just the next few years, and this kind of maxes out at 1.3 megawatts. There have been ideas in the past for doing substantial upgrades to JPark. They're each pretty serious surgeries. They're something like an 8 GeV LINAC or additional boosters and RCSs, and they don't have a lot of space for it. So those haven't been pursued recently, but they're kind of out there. So they're not being actively proposed. SNS is in the process of doing one of its upgrades up to a 2.8 megawatt capability, but that won't immediately be available for the target. And then I'll just wrap up, and then we can cover any questions on these if there are any. All right, so the HP report, the AF2 report status and plans forward. Those tables I showed you, we consider them a complete draft. I think we're going to eliminate a few columns to make them a little more readable, but they're pretty much in a complete and nearly final state. Where we have for the topical group report, we have a more or less complete executive summary, and then some notes in the draft report narrative, mostly about some of the white papers. That has to be extensively updated after this meeting. We, the conveners, we're soliciting comments here in person, offline if you want to email them to us, but we do have this mailing list, and the intent is that we'll report, the report, once it's complete, will be posted there with mechanisms for feedback in the next few weeks. And that's it. Any other discussion? No.
Thank you, Bob. Boy, so much work. All these tables and all these parameters put together. Yeah, thank you, guys.
It doesn't help when people forget how to use LaTeX too.
Yes.
I see Shekar over there.
And the questions can be asked from Zoom too. We can closely track Zoom.
A lot of work, but excuse me. So if you go back to your last table, first question is there a room to submit a quick white paper on what I'm about to say? So
okay. I'm just having a little tough time understanding you. There's echoes that make it hard to hear.
Can you hear me now better?
Yeah, I'd probably just speak loudly into it or hold it close to your mouth so there's more sound.
Okay, can you hear me better now?
Sure, yes.
Okay, so I was looking at this table, and as you know, I have worked on all the rings that you are trying to modify or PIP to LINAC. So I have a suggestion. Okay, yes. And suggestion is half written on that table. You have PIP2 going to 2 GeV, which is FNAL, PIU, LE 2 GeV. And then you have a FNAL, PIU, RCS going up to 12 GeV. And in your earlier slides, you talked about injecting at a higher energy in main injector. And main injector has this transition crossing around 18 something.
Yeah, a lot higher, unfortunately.
Yeah, right. So, and you want to reduce the cycle time. Okay. So why not consider a plan of 2 GeV LINAC and 2 GeV accumulator ring, which you call CPAR, and 2 to 20 GeV RCS, and directly over the transition helps you with emittance, helps you with the cycle time. You have already stripped it at 2 GeV, okay? And most likely, if you do it at this CPAR, you can make it as an accumulator ring and don't have to upgrade the recycler.
Sure. Well, so the CPAR is actually very small. Like it could fit in this room. So, but some kind of accumulator ring.
Yes,
But
but you
I
can,
mean, so, that's an interesting idea. I mean, I think people have talked about trying to get above transition
Right.
before, or moving transition down a little bit.
right.
And certainly there'd be a lot of advantages to that.
Well, moving transition down in main injector will be a tough job.
I'm sorry?
Moving transition down in the main injector, I mean, it's better to inject it above the transition in
Right,
main injector.
Yes.
So that's an idea. I'm willing to write one page on this thought.
Okay, some of the white papers are very short. So if you were interested, you've got kind of a month to do it. So,
Yeah, I can comment on that. Yeah, so we did look at it, and there's no reason why you can't go to 22 GeV if you just make a slightly larger ring. And yeah, one of the issues is it's not clear whether the maker will need it, because they will have a new gamma T system coming in the PIP2 era. So if that works well, but the issue maybe is if the charge density going through transition is too high, that you may get some different behavior. So one of the things we talked about doing in the PIP2 era is tell the booster to make as intense batch as possible. Just send one batch to recycler, one batch to main injector, and see what happens when you push the intensity in the main injector through transition. And that would tell us a lot. Right. Yes. So yes, it's not a new idea, but I think operationally it would be new to main injector. But yeah, and all the things that you said, you don't have to worry about transition. You have advantages for going higher energy. Synchrotrons are good at going higher energy. So there is some merit there for sure.
This is Chandra.
oh, he can't hear you, Shekhar.
So anyways, we did this exercise, Sean. We did this exercise. We have spreadsheets that show the options of going, building RCS that goes above it. We have options to show reducing the gamma T injection and then going above it. So we have lattices. We actually worked on lattices that will allow you to adjust the main injector gamma T lower and build an RCS above it. So all that has been looked at. We have tables on all those things.
This is Chandra. Hello. Can you hear me?
Hi, Chandra, can you let's Shekhar talk for a second.
So
Okay, sure.
other reason I suggested 2 GeV and because cost reduction, keeping costs contained is a big issue. Okay, so right now the PIP2 design, the way it's designed, if you go beyond 2 GeV, then you have to figure out how to put it into a circular machine, which is in the direction of main injector injection. Okay, because that is, bending higher energy will be more difficult. But if you look at the way the beam line we designed in that, which is going towards booster, you can continue to put the LINAC in that beam line towards booster, and you don't have to do any civil construction, which is a very costly thing to do in Illinois.
I think, that's a point that we've realized, the bending high energy H- beams is something you don't want to do more than you have to. And so in any case, whichever RCS or accumulator ring we're going to build, the PIP2 LINAC will have at most, or the upgraded LINAC will have at most one bend into that ring. And then that ring will be protons into the main injector recycler. So yeah. All right. Chandra, did you have something to add on this?
Yeah. In fact, the Shekhar mentioned that reducing the gamma T in the main injector is going to be difficult in the current configuration. But I think if we can change the quadrupole magnet circuits, just like the SPS has done at CERN, I think reducing the gamma T may not be that very difficult task, but it has to be looked into.
Yeah, I think that's the idea. Is they have separate buses, and so it's much more flexible than something like the booster, where you're never.
Yeah. So if we can make it much more flexible in the case of because I think as the Shekhar mentioned, having an RCS which goes from say something like 2 GeV to say 20 GeV or 22 GeV, that is really much more advantageous than going through the transition in the main injector.
Sure. Let's, I'll definitely incorporate some comments about this into the report. And if we have a white paper, that's even better. Sure.
Okay.
Okay. All right. So I see a comment from Bill, which I think is somewhat accurate, but is also overly cynical. So Bill, do you want to say something, or should I just respond?
Bill Barletta.
All right, well, maybe I'll just respond, but Bill says he hates to be cynical, but this discussion seems to be about a solution looking for a problem. And I think we're aware of that issue where we have, favorite technologies that, perhaps we want to employ just as much as possible. So we're aware of that. I'd say though, the less cynical way to look at this is how I was alluding to early on. And that is that these PIUs and the PIP2 and the PIU can start being considered as single purpose LINACs, that they're both to provide the megawatt and multi-megawatt beam to LBNF. And then Fermilab in its history of, trying to be being able to service multiple experiments at a time, wants to get the most out of these accelerators as possible. But, you'll notice with PIP2, we are building PIP2 without any other new users. The only user that will still be there otherwise is the mu-to-E experiment, which will use the existing beam delivery approach, and then also the high energy test beam area. And so it will just be maintaining the other capabilities. So we're not forcing anyone to have experiments.
Can I? First, I just want to say, I'll send you some updated numbers for CPAR because I think there may be some typo there. Yeah, so I think the power is probably 0.06 to 0.2. And then it's probably 8 times 20 nanoseconds. So
Okay, I took numbers out of the white paper.
yeah,
and
so I have to
did my
make
own
sure we're
multiplication.
doing, also make sure the white paper is correct.
Yeah.
Yeah, I mean, the general thing though, I would say is, yeah, you could build whatever energy you want, you could build an accumulator ring, and you could build a more compact version of the accumulator ring. So the question, two questions. Well, let me start with, so when you're discussing ESS, you mentioned part of the reason why they want to go to 2 to 2.5 is not just the targets and not just the space charge, but something about the pion production. So is the pion production per megawatt very steep at this part of the energy?
No, it reaches a maximum somewhere between 3 and 8 GeV. Okay, and this has been studied, and it depends on which kind of focusing collection channel you have. Whether it's neutrino factory, a muon collider, a conventional beam. So it depends a little bit on that. But generally there's a maximum between 3 and 8, maybe a little bit higher. But below 3, you don't produce as many pions. For just kinematic reasons. Being able to have enough energy to produce the pion itself. And above 8 or 10 GeV, you start getting into issues of lower cross sections and having to have longer targets, and then actually reabsorbing some of the particles you're producing. Also, some of the energy goes preferentially into really high energy pions, and so there tends to be a maximum there. There's for something like NUMMI or LBNF, there's other reasons to go to 120 GeV, what you might consider very high energy. That might be, in terms of just pure pion production, that might be 10 or 15% less efficient than the optimum, but it's much easier to focus it and get the higher energy neutrinos out of it.
But if I understand your comment correctly, it's hard to do it at 2 GeV or less with proton.
To make a beam,
Yeah,
especially.
yeah.
Okay, so when you look at something less than 2 GeV, it's usually going to be a decay at rest source. So they're going to make pions. It's somewhat less efficient, but then they just stop right there, and you only get the neutrinos from pions decaying at rest and then muons decaying at rest, which is a particular industry. But if you want to make a beam, a focused directed beam, yeah, you generally have to get above a few GeV.
Okay, and then if I could be permitted another question. So I was thinking about the subject of H minus laser stripping. We all agree this is a very important subject that needs R&D. And there's the SNS program for
Mhm.
at the 1 GeV. But if you want to go for higher energy R&D program, it's challenging because there's no H minus beam at the higher energy, so you can't do a demonstrator. So I guess the two parts is, one, is it useful to create the appropriate laser to show that it has the right power and the right time structure, but you have no beam to strip? Is that a useful demonstrator experiment? And the second is there any ion beams that we can strip? And it would be interesting. Do they even do that in the ion beam colliders or accelerators?
So I guess I would say that, yeah, this has been an area of research for a long time. I looked into it myself about 17, 18 years ago. Yeah, so we're not going to have an H minus beam of that high energy, right? That's just the case. But the physics of what's going on with the stripping, with the stripping the first electron, the excitation of the electron, and then the stripping of the second electron, it scales pretty well. Okay, and so I think we learn a lot from experiments at things like SNS energy or even JPark energy. JPark has a program on this as well. We learn from that, and then we do kind of the technology scaling into the wavelength of laser we want, and thinking about what the incident angles are. But actually there are some things that are brought up about when you get to really high energy. If there's HEV, you can think about not using the magnets at all and just using intense light beams to fully strip off the electrons. And that's very difficult to test because you need something like 24 EV photons in the rest frame, but at HEV, that's something you can make.
Mhm. Okay, so from what I hear from that answer is kind of the R&D path that we're on, which is give SNS what they need to do their experiments, is kind of the smart approach.
Yeah, I think you want to do it at the highest energy you can. I mean, the big issue that all this comes down to is the amount of laser light that's necessary. It's extremely large, right? SNS is getting to being able to strip a fraction of their beam to a particular efficiency, and not even on every pulse, right? And so, the scaling, in terms of the technology is, a factor of 100 or 1,000 away.
3 orders. Do we have questions on Zoom? I thought that Daniel and Bill and others had something to say. Zoom, anyone?
This is Chandra again.
Chandra.
Yeah. Okay. One question. In fact, Jeff Eldred and also Sergey Negetsev mentioned about the 10 hertz RCS. So my question is that, currently the harmonic number in the RCS, which is going to be very similar to a harmonic number, or the frequency is very similar to that, matches with the main injector, so something like 53 megahertz. Is there any way that we can basically reduce that particular frequency, having 2 bunches, 3 bunches in the entire ring, and then try to split that particular bunch at the top energy? If we try to use some sort of a long, little bit longer flat top at the top energy, is it feasible?
So I'm sorry, Chandra, I had a little trouble hearing you. Are you talking about rebunching the beam at high energy in the main injector?
That's right. Yeah. Say at top energy, that means, the rebunch at the top energy just before injection into the main injector to match with the main injector harmonics. Because then we can really increase the beam intensity significantly.
Okay, I guess I'm not exactly understanding what you're trying to do there. I will say that bunch rotation at high energy we did for antiproton production. It was advantageous there. You would certainly do something like that for a muon collider, although I'm not sure you would use 120 GeV beam. For the neutrino experiments, it's actually, for the most part, not necessary. there are some new proposals, they call them, stroboscopic or time of flight experiments, where they would like very short beam pulses to gain some timing information in the detector. But that's still kind of at the very early proposal stage.
Yeah.
Did I
Okay.
answer where you were going? I didn't really see the opportunity for higher intensity.
No, actually, okay. So the opportunities for the higher intensity comes from if we are running at lower harmonics. For example, JPark, they have got harmonic number is equal to 1, right? So because of that, they can really put a very large amount of beam. The bucket size is so large.
Yeah.
But
Yeah.
they can.
Okay, now I know what you're talking about. So
Yeah.
this is about the advantages of going to low RF frequency, like JPark did.
That's right.
And
But
that
the,
is a potential way, I'd say there's a number of downsides that make it very difficult for us. One is that, with these very large buckets, you have to have a larger longitudinal acceptance in your ring. And I think that would be an issue for us. The other is so JPark makes use of these extremely low Q wideband cavities that are incredibly stable for beam instabilities. But the technology only works in the few megahertz range. It doesn't work up at 50 megahertz or so. So yeah, I think we've identified in the past that there could be some advantage to going to low energy. The disadvantage again, though, is that those RF cavities are extremely power hungry. They're almost just resistors being switched back and forth. So the power consumption of the RF would go up very substantially. And then for us, the issue is that all of our RF systems would need to be replaced. So you need to have, more or less the same bunch spacing throughout the complex. And so every ring has to have the same kind of, boosted frequency. And so we'd have to replace everything. Other than that, I don't think anyone's looked at it too seriously.
okay.
Okay, thank you, Chandra. Yeah, please go.
Yeah, I was wondering, you said that some of these options potentially allow for a faster cycling of the main injector. Is it known what the maximum, the target, I guess at 2.4 megawatts, we don't really have a target and horn designed, exactly anyway, but is that something that might be taken into consideration is, 1 sec, trying to make sure we understand the cooling effects at, a 1 second cycle instead of 1.2.
Yeah, I think it certainly needs to be looked at. I believe in the past, we had an earlier proposal years ago. Part of it, so when we did the Nova upgrade, we had, what was it called, SNUMI phase 2. And part of that was trying to push the main injector cycle time down to 0.7 seconds. And so it is at least conceivable. The magnets actually tend not to heat up as much because they're just I²R cooling. And so if you're ramping them down quickly, the magnets don't get that much hotter. What's needed is wholesale replacement of the power supplies, and then that increases the voltage between the conductors. And so you have to worry about breakdown of the magnets. You have to pay for all the power supplies, and then you have to make sure you have enough RF acceleration to be able to do that. So you probably need more RF as well. But so it's not for free, it's not cheap, but it's on the scale of cost and complexity that it probably should be looked at to see what we could get out of it. I'll remind you, we've already shrunk it a lot, right? When we started NUMI, when it was a NUMI only mode, we were up at 1.8 seconds or so, and we pushed it down to 1.33 for Nova, and we've since pushed it down to 1.2. So we've already gone almost a factor of 2.
Okay, we have 2 questions from Zoom. Bill, please go ahead.
Yeah, so this will sound confrontational, but that's okay. It seems to me that that absent any physics case for the 2.4 MeV megawatt operation, except for the neutrino program, it seems like the reason to spend $1 billion to do that is because otherwise JPark beats the US to the interesting neutrino physics. And then I ask you why, what's being done for people to look for any science case beyond that? My Hadron friends tell me, oh, geez, it's that neutrino physics is not deep enough to warrant that much money, because that gets the cost of the whole Dune LBNF up into approaching $5 billion. And that's an awful lot of money. So I think that you have to make a strong argument about why you need this in the race against the Japanese. And if you don't make that, the special pleading that, hey, we don't have users, we better get users, I think that's out of place at Snowmass. This is going to be a science case driven activity. So now tell me why I'm wrong. I mean, I want to hear, I want to be wrong. So tell me why I'm wrong.
We're going to have Jeff Eldred from the audience. He'd like to give a response.
Yeah,
first.
so this idea of we don't have users, it's true in the sense that we don't have users locked in and planned, but we have many proposed users and they can become real users. And it's something that we've looked at very carefully over the last 2 years. It's something where even at this conference, we're starting to kind of settle in on ideas. Some of the users are at the GeV scale, in which case you can make the case that it's slightly separate from the 2.4 megawatt upgrade. But in particular at 8 GeV, you receive a lot more beam, regardless of what path you take to do the main injector upgrade. You will receive a lot more pulsed beam at HF. So in particular, you look at doing dark sector search, you look at doing KDAR or K-pipe, and then there's even discussions if you are on the ambitious side of doing something that's going to help you build towards the front end of the muon collider at 8 GeV. But we are really happy to take other users, and that's part of our message is the physics potential is high at 8 GeV automatically with the 2.4 megawatt upgrade of the main injector.
But
So that's fine. Do you have any idea of how much of a program it takes to establish in the user community to make that case? I mean, we heard a lot of pleading yesterday that there's not enough of a user program beyond Dune for the present PIP2. Now you tell me there's a lot, and I don't doubt you, but it seems that really has to come out. That really has to come out from the user community at this work, at this Snowmass, from the science, from the particle physics sides. As for the muon argument, I don't buy it. The big thing is you don't even know whether you can store muons and manipulate them in a ring. Until you do that at whatever energy, even at a GeV, you don't even know that that's a viable concept. So I don't buy that. I want to hear a physics case, not an accelerator case.
Or 3 GeV muons with abandon, right? For the G-2 experiment might not be the type you're looking for, but that has been done.
At low intensity.
Yes. Yes.
Yeah, that's not the problem with muon colliders. It's
Yeah.
like mice. Mice is not a real, it's a cooling experiment in the sense that a counting experiment is a cooling experiment. You don't know whether you can cool intense beams.
Sometime, Bill. I
Well,
don't think
But
it's-
that's a different argument than this one. That we should take that one offline.
Yeah. Shekar wanted to say something.
Vladimir, you want?
Or Vladimir? Or-
May I second Bill's concerns? Even previous P5 told us that there should be good balance between large scale, medium scale, and smaller scale experiments. What we see right now, that there is a significant strategic conflict between the dreams of big experiment like Dune to go to higher power, more kiloton years, megawatts, and so on and so forth, and desires of others. So they essentially, if you bring it to the essence, it's either we invest in the 2.4 megawatt upgrade and the LBNF Dune phase 2, or we have time or have support and money and effort to go into collider world and all kind of experiments at, for example, with PIP2. So as we learned yesterday, there were 72 proposals in the rare processes frontier. Eric, I'm about right. So 70 proposals of various experiments. About half of them would love to have PIP2 used. But contrary to neutrino physics, which is well organized, projectized, so they know what they want, and they have a good chance of getting what they want, the community of rare processes frontier physicists is not that organized. They can't clearly spell out their priorities, and they feel that they will be killed by neutrino. Same feeling is shared by energy frontier guys. They think if we proceed with this neutrino path of 2.4 megawatt upgrade, extra 20 kilotons in new detector, that's indeed will make life miserable for the next basically till 2040, right? So one big experiment in that case kills everything else around, and that's the biggest concern. So question is, maybe Bob and your community, your accelerator frontier topical group too, maybe you talk to neutrino physicists more. Do they have plan B of any kind, which will be a little bit more forgiving to small experiments and medium type experiments, medium scale at 8 GeV, at 0.8 GeV, PIP2 experiments?
Well, so I can kind of give you my perspective, and this is also answering Bill's question. And so the neutrino frontier or neutrino experiments, they have their goals. They have some pretty well-established goals of things that are out there ready to be measured. Things like the mass hierarchy of the neutrinos and the CP violation. And those are pretty extremely well-defined targets that these experiments can measure. And so that makes it very well motivated, because at the same time, it's a detector technology that the experimentalists love and is extremely flexible. So there's all kinds of other neutrino physics you can do with it. There's even things like atmospheric neutrinos and supernova neutrinos. That's a very high priority as well. So it checks a lot of these boxes of new physics, as well as new physics that we know is absolutely out there. And that's what the mass hierarchy and the CP violation are. Personally, when I look out in the field, I only see one other thing like that, and that is dark matter. Okay, from astronomical sources, we know 10 different ways that dark matter is out there. Okay, we know it's out there, and it's probably a particle or something similar to it. The problem is we don't have kind of one experiment that we know can go out and measure that. Maybe it's supersymmetry at the colliders. Maybe it's all of these dark sector fixed target searches we're talking about. And ideally, you would have some kind of systematic search that could look into all the possibilities, because that is definitely something out there, a puzzle that needs to be figured out.
But okay, takes dark matter. Do we have any solid proposal for dark matter that is a kind of on the front runner among all these 70 other proposals, which we can as a community push as something definitely to be done?
Right. So I think that's the challenge that you started out with, is that there's no consensus
among them.
And similar with the colliders, there's no consensus in which direction to go there.
Yeah, but for the dark matter, you have an enormous range of masses for which there are plausible cases. And there is no giant, I would claim that for those dark matter experiments, there is no single large facility. There are many small experiments that need to be done to sort of tighten in the exclusion regions so that there can be a larger medium scale definitive experiment. But I think right now, I mean, there is such a wide range of possibilities. I can't conceive. I've listened to a lot of dark matter talks over the past year, and I haven't heard any one experiment that can explore the whole mass range that are possible.
Yeah, you're right. I mean, that's what would really, if we had that experiment or a series of experiments or a facility that
you'd propose it.
Yeah, but we don't have that.
Yeah.
CERN have it. Does CERN have the dark matter experiment of good quality?
There are lots of dark matter searches.
There are lots. There are lots, Vladimir.
I mean,
They should be done. They should be done. They're run by relatively small groups. They're great training for the students and postdocs that are around them, rather than big giant experiments. So I think that, and I think,
so Bill,
as to the first point, Vladimir said it much better than I did. So But I think that that's the issue about looking for a big range of experiments of moderate scale that can be fed with facilities that we have. Really exploit the stuff we have. Because to be realistic, we're not going to get a lot of extra money. We know that. That happened the last time. So, and we don't want to have the answer. We don't want DOE to come back with, well, this is great to have a collider activity, but what do you want to kill? We don't want that response. So we have
Bill,
to
that
make the
is what
physics
happened.
case so compelling that it's very hard for the new director of HEP to say, well, you tell us what to kill and then you can start this. We have to have really compelling science cases.
Yeah, but Bill, what happened after, the last P5 did say support small, medium, and large projects.
I know that.
But large project ate the medium and the small projects.
That's what Vladimir said, exactly.
And about the physics program with 2 GeV and 8 GeV, and all of those are very well outlined in the document where the original Project X physics was made. And I have seen all of those slides even presented at this conference.
Yeah.
So
I'd like to get to Edward, and let me just say one thing, and I think the funding agencies would tell you this too, and that is that they have maintained a large suite of small experiments. We might not notice them as much, but there's several of them at Fermilab. That's what SB&D is. That's what
Yes.
Icarus is. That's what Microboon is. There's a lot of them underground, that are being done. In fact, what usually happens is these large projects like Dune, they occasionally get delayed, and then there's a bolus of money that is available and supports a few smaller.
but those are
experiments.
all in neutrino physics.
No, there's a lot of dark matter experiments as well.
Right, but see, with this beam, if you have a 2 GeV or a 2.5 GeV beam, you get into kaon, you get into eta, you get to all kinds of rare decays, which has been proposed over and over again at Fermilab 10 years ago. For 10 years, all of those folks have just left because they have no chance of getting their experiment approved. But if we have a beamline and we get those users back, there is a chance those physics has not been done in the last 10 years.
Okay, that's what we wanted for SNOMES. All right, let's go to Edward. He has a question.
Hello. My question is actually more technical. I would like to return to a previous question that Chandra asked. I'm not quite sure, and this maybe I missed part of the question, but I wasn't quite sure. So Chandra was asking a question about lowering the frequency to go to very low frequency. I definitely see some advantages maybe to that, and I understood Bob's answer. That's true, but don't we have a fundamental issue with this, the frequency of main injectors, that you have to have bunch, essentially bucket to bucket transfers and everything, essentially just match buckets in different machines. The reason I am asking this, I mean, in principle, PIP2, if it operates for LBNF and for other machines, I mean, then it has to have this chopper, which pretty much requires the front end to run at the factor of 2 higher frequency, plus all this fast chopping is kind of sensitive device. And so there are a number of complications, technical complications. It works, we demonstrated it, but especially expanding it in CW regimes might be complicated. So going with one lone pulse, definitely it's much easier, I mean, from the Linux point of view, but I'm not quite I mean, if you don't have the bunch structure injected into the machine, how are we going to do the bunch, I mean, like transfer bunch to bunch? Maybe I misunderstood the question.
Okay, Chandra is here. I can respond.
Okay, go ahead, Chandra.
Okay. In fact, the way how I'm basically thinking is that from injection energy in the rapid cycling synchrotron, from injection to the top energy, we will go using the single bunch or 2 bunches type of scenario. Okay, and then at top energy, you split. So that's why I was saying that if we can have a little bit longer flat region, this has to be investigated, how long it has to be at top energy, then that's where we want to split the beam which will match with the main injector frequency.
You mean you the diabatically bunch it?
Yeah, that's right.
Okay, so you are going back to pretty much adiabatic bunching idea.
Yeah, Edward, this kind of thing is done in places like CERN. They actually do the opposite. So they have long bunches coming out of their booster, and then they shorten them to go into the later accelerators. So this sort of thing is certainly possible. It's sometimes lossy. So
Yeah, that's a question.
you need to worry about that.
No, actually, in the case of the in the PS, in fact, they do all the RF manipulation, but the beam cycle in the PS is really very long. So we should remember that one. But at the top energy, it is really that long at all. Its early part it's longer. Now, the beam losses in the PS, not the PS booster, is really insignificant. This is my recollection. And in fact, when I was working, when I was there, this is what I basically noticed. Certainly there is a big loss in the PS booster. PS booster it's a smaller ring, but in the PS itself, the energy loss is really minimal. If anybody is from the CERN, they can basically respond to that one.
Okay, I know. I understand now. I mean, I guess it's a question of numbers, right? I mean, you can build a refused adiabatically bunch with 5% loss, and they can. I mean, system is the same, right? I mean, they can bunch with 99.9%. So, okay, now I understand what you're talking about.
Okay, thank you. Jeff?
Thanks.
Well, not to go back to the previous conversation too much, but I don't think anything about doing booster replacement or PIU precludes participating in an international collider program that may be there, or doing smaller medium scale experiments. In some cases, there are synergies. On the dark sector, I think it's a valid point that you can't just go to one dark sector experiment and say, yes, this one's going to find dark matter and probe its properties. But I do think that dark sector experimentalists are very excited about the suite of programs that we have proposed at Fermilab. You can draw a circle around the GV scale dark sector search, that 8 GV, and there's also 120 GeV slow extraction experiments, and then there's dark sector physics that you get at Dune. So we have this very large, very robust neutrino community at Fermilab. We can have the same thing for dark sector, that these different experiments can talk to each other, and we can develop a real in-house expertise on this question. And so I think that is an exciting physics program. People say, well, why do we go to higher energy and colliders? Because we haven't checked to see what's there. Well, why do we go to more feebly interacting particles? Because we haven't checked to see what's there. So I think it makes sense to push on this frontier. It's not the same as measuring parameters of a known, measuring parameters that we know to look for, but I think it's an exciting physics program.
Jeff and Bob, maybe you can then tell us, there is a strong sentiment right now in the troops that we are building PIP2 and utilizing only 1% of its intensity. Why don't we kind of put some effort in utilizing the remaining 99%? And what would be the champion experiments or beamlines to get there?
Well, I think that is the leading question, right? And in fact, choices were made, over a decade ago to build this machine in a way that was more favorable to other experiments than it was to LBNF. If you wanted to build this for LBNF, you would not have built a CW LINAC.
Maybe not superconductive.
And perhaps. Okay, so decisions were made not for the benefit of the neutrino experiments. They were made for the benefits of other experiments and technologists.
And now we don't have other experiments, obviously, because they have no money. Right?
Yes.
It's not an issue. I don't think necessarily it's an issue of money there, actually. I think it's understanding what experiments are needed. The most excitement at the GV scale has been the accumulator ring experiments, which they need high enough duty factor that they can get significant power, but they don't necessarily, but what they want is concentrated beams, so they don't necessarily need the CW. So the question we thought we've started to look at is, okay, what duty factor do you really need? You maybe don't need CW, but maybe you need as high current as you can at 5–10% duty factor. That seems to be a better fit to what the experimentalists want if you're building a series of one accumulator ring or a series of accumulator rings. There's the dark sector thing. We also mentioned, I should also mention that there's this Enigma or Prism AMF charge lepton flavor and violation program that also wants an accumulator ring with short pulses. So I think the consensus on the GV scale is not looking like what you might have thought in the Project X era, but there is experiments there.
Yeah, a couple of things I mean, the BIP2 was built with all this extra beam power, but nobody asked for that. Like nobody wants a CW 1.6, at least. I mean, ADS is the only thing, ADS is the only community that would want such a beam. So, it was kind of a build and they will come. And as I said yesterday, it's like in Field of Dreams, if you built a baseball field and nobody showed up, which is what would happen if you listen to voices in your head. But I could be wrong. I think the only or the most mature proposal is the MUTA-E2. Like there is a plan to use the PIP2 beam with no modifications, but of course you end up using 100 kilowatts of it just because you're building. So I do think, there are these other experiments, and I think Matt Toops did a good job in the beyond booster replacement. But, this is where, the PIP2 beam is what it is, and we need to find more uses for it. There's also been we wrote a white paper many years ago about a slow muon program that could compete with PSI or Triumph, and it's not high energy physics, but it is a user community and it's people who are interested in it. Very competitive. We direct beam directly from the BIP2. But then, now we're talking about these various accumulator ring ideas, and the different possible experiments are very different demands. What you would need to drive an FFA is a very challenging accumulator ring compared to what you would need to drive a dark matter experiment. That's a fairly simple accumulator ring. And where you make that energy break is also interesting. Where do you put like you say, you clearly want to increase the energy of the LINAC portion to get into the Kaon community. I think you would you pick up a huge user community there. And again, Kaon community doesn't need particularly challenging beam structure.
Where are the white papers though, for Kaons?
There's a lot of, yeah, I mean, there's a chicken and egg problem here. I think.
Yesterday we had the first meeting of all frontiers in one room, basically. And they asked, basically, all frontiers said, what we are after. And we said, yeah, we'll help 2.4 megawatt upgrade. And then we mentioned the Pelic accumulator ring, and rare process frontiers guys didn't say that they're so supportive of it. So I just totally puzzled. So what do these folks need? Again, from our perspective, it will make a lot of sense. It's yet another opportunity to use significant chunk of PIP2 beam for something related to big question like dark matter. And the enthusiasm is, I would say, limited at best. I don't know, where's the disconnect?
Well, I think part of the disconnect is them not understanding the problem. I mean, they maybe don't understand the nature. They hear the energy, but they don't understand the time structure, and I guess that's on them. But I don't know the answer. I'm just kind of articulating what I see as the issue.
Snowmass is supposed to be the place.
Right. I think, and I said many times in mine, this, a lot of this stuff runs on rails. LBNF is going to do what it does. The LHE is going to do what it does. The ILC people are going to keep asking for what they always ask for. But these are places where we could really have an impact and make decisions.
I mean, I don't know. I would like to contribute to this also discussion, because I mean, we are saying that PIP2 doesn't have other users. If I look at the global requirements for PIP2, I mean, which I'm aware, I mean, very closely because they drive pretty much my design. They specifically say that the machine will have to support MUTA-E2, which is pretty much requiring CW beam at this moment, CWRF, and then pulse beam with 100 nanoseconds, and then you have, of course, these gaps. And we looked with Eric Prebis several different scenarios. In principle, we can, even with the same beam parameters, we can feed, if we don't chop the beam during 100 nanoseconds, we can provide 200 kilowatts. That's not a problem, but the question is, we can take it. Also this gap, 1.6 microseconds, you can, if you use RF separators, you can provide these beams to other experiments. Essentially, we can send the beam to other experiments, but even mu2E2 by itself requires pretty much CW beam. So I wouldn't say, I mean, and it's a requirement for the project. I mean, that's why I don't think that we should say that we don't have at all. I mean, anything. I mean, it's not the beam is not really, I mean, there are no users, right?
So
if you tell me that mu2E2 is not going to happen, it's a slightly different story, but
Yeah, I didn't mean to imply you're not supporting mu2E2. I mean, yes, we that was considered early on in our planning. I'm just saying that as far as I know, we're the only users of the beam at straight out PIP 2.
Mm-hmm. Right. No, I fully support it, and I sent this email yesterday that we should definitely, the more users, the more the merrier. That's for sure. I mean, we should try to serve people as possible and get the community organized for sure, 100%.
So beam and physics is like a chicken and egg problem. Okay. I don't know how many of you remember that 8GV physics program from Booster was not there till Jerry Jackson decided to produce anti-proton with that beam. And he tried to extract the beam, and then all of a sudden a whole neutrino community came to start using 8GV beam. Okay, so it's kind of like, if you say that I have 2GeV proton beam of this power, there are at least 10 experiments I can name right now which will come up and say I can use this beam. Okay, so we tried this 10 years ago. We need to try this again. That we say, okay, we can give beam out at 2GeV with these parameters, 8GeV at these parameters, 20GeV at these parameters. And I can tell you that there are community out there, but yes, you have to say that, look, there is a finite probability that this beam will happen. Not 120 GeV beam will go to LBNF and Dune target, and rest of you are out. So then people are not going to come and waste 10 years of their life. Okay, and that's we need to, the accelerator side need to engage with those community and say, look, there is a finite probability that we can give you this beam. Okay, and I think there was on your previous slide there was a bunch of physics thing, but I thought that they're not in this one. You had a physics table. Yes. And you I think you should include some of the things I saw on the rare decay table. At least my favorite experiment was missing from that table. That's why I tried to. Yeah, so if you go to the rare processes meeting 2 days ago, you know, this is, well, I see there is a kaon, but there is a eta physics, rare kaon decay, a lot of, and there are Fermi-Lab physicists who are involved in those things, but they don't say anything because they see there's no possibility of having those beams.
All right, should we take a break? We're actually over time.